Hello, Build Stuff. In a change to your scheduled programming, we've had a couple of speakers who've had to cancel or couldn't make it, so we've moved a couple of things around. So please, welcome now on the alpha stage. Security is one of those things that I don't know if any of you has ever inherited a code base with the plain text passwords and the firewall wide open, or even just the thing where you're like, it doesn't work. I know, I'm going to right-click the folder, everyone full control, let's see if that fixes it. Security is hard to get right. And there are some things that all of us can do as developers right from day one, from the first line of code, to start baking in security, cryptography, best practices. And to tell us all about that now, please welcome back to the alpha stage, Oren Eini.
Thank you. At one point, I used to start coding interviews and job interviews in general with the following screenshot. And I intentionally don't show you any code. I want you to imagine that. Public class, base controller, one field, public static bool is admin. Take a moment to consider that. If you cringe, you move to the next stage. If you didn't, try to imagine what happens when an administrator logs into the system. Now, it sounds like a really, really stupid thing to do. The problem here is that we are here to build software. And security is a tax. No one likes to pay taxes. Unfortunately, it's a tax that requires to do quite a lot of really complicated things. You need to understand math, and all sorts of other crazy attacks that no one ever heard about. The point of this talk is not, let's roll your own encryption. This way lies madness and someone and a cat in your database playing chess with itself. So let's talk about the primary issue. And the primary issue is that we have to provide secure systems. But most of us are not security experts. And even security experts have bugs. It's very, very interesting. There used to be a worm, I think like in the past 3 or 4 months, that injected itself into machines through buffer overflow in McAfee antivirus. Kind of a problem. And this is not a single instance. And the problem here is that the moment you have a single weak spot in your system, someone gets in and it's game over. Now, why is it so hard? I mean, put a password. Who cares? Well, it turns out there are lots of details. And I love to give the example of airports. It used to be that you could go to the airport, you could go to the gate, you say bye-bye, go in, and then there was the whole 9/11 thing, and they started taking security seriously. So you have to take off your shoes, you have to wait in line outside, and if I'm the bad guy, I take a bomb, please don't tell any security guard about that. But if I'm the bad guy, I take a bomb, I go to the airport, and instead of putting the bomb in the airport, I put the bomb in the queue. Same exact thing, same exact outcome. It makes my life easier. I don't have to board the plane. So a lot of that is about security theater. You hear about the notion of military-grade encryption. And here is the really, really sad thing about military. Military goes for the lowest bidder. That's not a compliment. And when we talk about security in general, we have to consider what areas do we want to tackle. So we have encryption. And encryption is about you and me exchanging messages in such a way that someone else can't hear that. Now, me asking my wife, how was the play for my daughter, is not something that would assume most people would consider interesting enough to eavesdrop on. But my conversation with the bank about, hey, I need to pay some salaries, move money from this account to that account, is probably more interesting, especially if they can figure out what my password is. Which leads to the next point. How do you manage passwords? And how do you manage authentication in general? Because just knowing what the password is doesn't help you to know whatever it's me, because my password is swordfish. Anyone can say that the password is swordfish. It used to be at one point a really well-designed system, they put a unique constraint on the password. And then they give you an error. So this password is already in use. Yeah, anyway, so we now need to talk about authentication, which is separate from passwords. Remember that. Certificate, so how do I know that you are who you say you are? And in basically, you get to a really crazy place where you read a security paper, and it starts from assuming that the enemy has a full control of everything in the middle, and they have the ability to do some pure mathing that no one really understands, and then they can do a whole bunch of other stuff, and finally they have managed to extract 1 bit of your secret key with a probability of 32%, and this is the shocking news, and now we have to replace our entire security infrastructure. This is not about that. This is about not leaving your door unlocked. And before we do that, we need to understand what it actually means to talk about security in modern world. So let's talk about the first thing. Most of you have gone through computer science training. They learn about RSA, public key encryption, take P and Q, they should be large primes, and then take your security and please shred it, because if you do that sort of thing for anything other than pure teaching moments, you're doomed. I used to work for a company that dealt with payroll, and payroll is somewhat sensitive. So they had this really interesting scheme, and they were really secure. They had a hand roll encryption scheme written as a native VB6 DLL running in 32 bits. Now, it was so secured that there was 1 copy of the source code for the encryption algorithm kept initially in a floppy disk in the chest pocket of the head developer for that product, and he used to take it home with him. And obviously I said, this is insane. I said, oh, no, this is okay. He uses a USB key now. That was certainly security, job security. So the hard rule and hard and fast rule, never roll your own security. Always use the security built by people who actually understand that. The number of that is very low. So you go with the most popular frameworks because they've been reviewed, the sort of errors that you will run into has already been discovered, etc. So let's look at the first thing. In theory, there is an unbreakable encryption mechanism. Take a one-time pad approach. Generate a stream of random bytes. XOR that with your message. So do a binary XOR on the message, and it is mathematically proven that no one could ever break that encryption. Okay, we're done. No need to go anywhere, right? 2 problems. Problem number 1, how do I distribute that one-time pad? So let's say I want to send you a picture of this water bottle. I'm assuming in modern phones, this is about 5 megabytes. So before I can send you this picture of a water bottle, I have to first send you in some secure manner a 5 megabyte one-time pad. And it's in the name, it's a one-time pad. If you use it even once, it's okay. If you use it once, it's okay. If you use it a single time, twice, do you know what happens? These things happen. Real photo of a spy being arrested. It is a catastrophic failure of all encryption properties. Another thing that we have to understand is, and this is a critical issue in cryptography, is the notion of randomness. Pretty much every security algorithm requires you to have a secure manner to get cryptographic quality random bytes. If you're using C#, there is something like that from the random number generator from cryptography. If you're using Linux, read from dev/urandom or something like that. Do not use random. Do not try to make your own. You will fail in really interesting ways. So let's avoid that. It will become really important later. But for now, let's focus on how to avoid this scenario. So I want to be able to share some data with you securely. I can do that with a one-time pad, but I can't, I need to first give you the pad in the first place in a secure manner. I might as well give you the real results at that time frame. So how do I do that? So one way is to schlep you a physical disk in some secure fashion with 1 terabyte of random data, which we can then segment and get, but you know, I'm talking to you a lot, 1 terabyte is gone very quickly. So we want to have some other alternative to do that. So what happened if I had a seed that could generate an infinite number of random values? And if you and me, with cryptographic strength, this is important, if you and me are now running together on the same seed, we generate the same set of random-looking bytes. But anyone who doesn't have this seed wouldn't be able to reproduce that. This is at the heart of modern cryptography, where the most interesting detail is whatever you can recover from the encrypted values, anything about the key, anything about generating additional, the rest of the key string that we have. But this is still a problem. Here's what happens. I'm going to use the seed to send you a picture of this water bottle. And the seed can be 32 bytes. Awesome. And then I want to send you a picture of this adapter. What just happened? I use the same seed both times. I generate the same key stream, same one-time pad. I use it twice. It's game over. At minimum, because I saw the key stream, the secret key stream with this and with this, and I have an attacker can have both encrypted values. So if it XOR both encrypted values together, you end up with the XOR result of the two. Basically what happened is that we XORed away the secret key and we are left with the output, with the XOR output of the two plain text, which means that now we are able to do all sorts of interesting analysis on the key and extract everything out of that. Basically, catastrophic failure. And again, I don't want to get into too details how we actually do that. So we need some other way of doing that. And the way to do that is to do something called either an initialization vector or a nonce, where nonce stands for number only used once. Really, really important, only used once. And the way that it works, we do this. The stream that we generate use the key and the nonce to generate a different output. Now, when I'm sending you the encrypted value, the first thing that I need to send to you is the nonce. And the nonce is just, it's not secret, it's public, it's part of the encrypted value. And with the nonce that I generated and the key that you already have, you can now generate a different key stream each time, preventing the key stream reuse and the catastrophics that result out of that. And now we're good. Yay! That was 10 minutes on encryption, but hey, wait. Now we have something called encryption modes. There is AES, which stands for Advanced Encryption Standards, and it has different modes in which you want to use. And unless you're a cryptographic expert, you say, oh, electronic codebook looks like an interesting details, and then you encrypt using that. And then you have this very famous picture of the electronic codebook penguin, because it encrypts separately each and every 16 bytes block. And you still can see the penguin. Sucks to be that guy. So now you have to consider, how do I actually manage that? Because, okay, I have options and I have details and they actually matter. And if you're not a security expert, it's really hard to understand what's going on. Modern security practices do not give you choices. Modern security practices you want to use for secret encryption, for sending someone sending details securely to the other side. You want to use either ASGCM or XCHA Poly 1 something, 1305. Why? Those are composed primitives. This is a complete solution that was intentionally designed to be actually hard to misuse. This is a really important property that came out of a lot of experience of giving developers all of the primitives and having them compose them together. They compose them badly. So don't have any choices. You want to use AES or XChacha, and it matters, not just AES, GCM, XChacha, Poly 1305, etc. Another thing that is important is that they have different size of nonsense. And it is indeed a lot of nonsense, but it matters. So for AES, you have 96 bits. For XChacha, you have 192. Yeah, does it matter? Turns out that it does quite a lot. We'll see exactly why in a bit. Another aspect that we have to consider is, along with the encrypted data, I may want to send some data about the message itself. Maybe its position, maybe its length, stuff like that. And I need to, for example, I may want to send that this message was sent from this IP. And obviously the IP is not a secret, but I want to make sure it's not spoofed. So I can include additional data with the message that is sent as plain text, but I still want to verify that it was sent for me originally. We'll see exactly why in a bit. So let's look at this. How do I use that? So I'm using AES. This is C# code, and you can see I have some output here that certainly look like this is encrypted. Now there is a problem. Look here. I'm encrypting a cookie that I'm going to give to you, and at a later point in time, you will give it back to me. And I'm happy because I would decrypt it using my key. If it's valid, and then I know that I encrypted that, and I can trust it and move on. The problem here is that we're using malleable encryption. What does it mean? Look at the top. I encrypted this value. Roles is user, blah, blah, blah. And now, here is what the middle code is what the attacker is doing. And I'm getting some blob from the user, from the server. And this is an encrypted blob. I have no insight in what's going on inside it. But what I'm doing, look at the for loop. Inside that, I'm XORing values. And what happened is that XOR is transitive. So what I'm doing here, I'm XORing the old role, the admin, and the users. And I'm basically replacing those values. When I would now go and decrypt the value, it would successfully decrypt into a cookie that says that I'm an admin. And then you know what happens? Yay! I'm in your database and I'm having fun. This is a real attack. I think Ruby on Rails had that like 7 or 8 years ago. And it's really easy to make that mistake. Why? Because this is the sort of code that you write. And it looks okay. And don't do those sort of things. Go and use the highest level primitives that you can do. Don't compose encryption. And again, AES, GCM, and XChacha Poly handle that. And how do they handle that? They handle that by also signing the encrypted message. And the idea here is that when I get some encrypted text to decrypt, the first thing that I do, I'm going to validate that the digital signature that was generated is the same. And if someone tried to do something like this, where they modify the encrypted text, it would be detected and aborted immediately. And now we still have another issue. You have to use nonce number only once. What happens if you reuse that? For example, what happens if you use 1, 2, 3, 4 as the number and someone rebooted the machine? What happens then? Well, it's fun because I'm using the word catastrophic failures a lot in this talk. And it's true. Because in AES, you expose the message. You assume that you expose the XOR of the message. the plain text of the message. It also allows you to expose the message with a little bit of work. It's giving you a lot of information about the key. So if you have multiple such cases, you can recover the secret key being used. With Ekchacha, it's basically expose the message XOR, which expose the message eventually, and most fun, poly 1305 means that you can extract the key used there and forge messages, which brings you back to this issue. So this sucks. But remember that I told you about the size of the message, size of the nonce? So with AES, the AES GCM, the size of the nonce is 96 bytes. If I'm generating that randomly, I have to face the birthday problem, which is in this case 2 to the power of 48, which is apparently not secured. If I'm using Ekchacha, then the nonce size is 198. And even with the birthday problem, it's still considered to be secure. And the best way to generate nonsense with Ekchacha is just get me cryptographically random bytes. But we still have problems. Therefore, we have the notion of sieve, standing for synthetic IV. And the issue is very simple. It says something like this. Instead of using a nonce that the user provided for me, I don't trust the user. So I'm going to take an additional step. And what I'm going to do, I'm going to generate a nonce from the message, the additional data, and the nonce that the user provided for me. And this has a really interesting property. What happens if I have a fixed nonce? Then if I'm encrypting different messages, the output of the hash function here, the cryptographic hash function that is used, would give me different value during the encryption process. So that would actually mean that I have separate nonsense. If I'm sending the same message with the same nonce, I would output the same message. But at least at this point, the only thing that the attacker would be able to tell is that I'm sending the same message as I sent previously. It wouldn't be able to tell anything else about that. This is about encryption. Now we're going to move into another topic that is of a lot of interest, and is how do you deal with passwords? And it used to be the case that you put password in your tables as plain text, and you compare to that. And people then cried, and there was a lot of anguish. So they put it as an MD5. And then people realized, hey, MD5 is insecure. So now they put it as SHA. SHA 1, 2, 256, stuff like that. And then they realized that this is really, really, really stupid for one simple reason. Do you know how do you construct a cryptographic hash function? There are a lot of requirements. You have to avoid pre-image attack. You have to avoid a whole bunch of other terms. And unless you're into cryptography, you don't care. But what do you care about? A cryptographic hash function is designed to be fast, because that's what you want to use it for. So now we are in an interesting position. Given that I have a list of the million common passwords, and I have a hash function, I have a hashed password, how long is it going to take me to reproduce that? Almost nothing. There is Hashcat, and Hashcat can process about 8 billion hashes per second. I'm using salt, I'm using pepper, 8 billion hashes per second. This is in no way, shape, or form secure. So what we actually have to do is something completely backward. We have to use an encryption, a hashing algorithm that is actually meant to be slow. And one of those hashing algorithms is called Argon, Argon 2D, Argon 2DI, it doesn't matter really that much. And the interesting thing is that it is meant to be slow on multiple axes. So you have the amount of memory that it uses, because memory is really expensive. If you need 256 megabytes to compute the hash, then you generally aren't able to use thousands of them at the same time. You have the number of iterations, the number of threads, and you can see more or less how much time this takes. And this leads to an interesting problem. I'm using a hashing algorithm that is designed to be slow, that is designed to be actually problematic to use. And you know what happens? Now I have set up the perfect scenario to cause denial of service on myself. Because think about that. All I need to do is try to connect to the server with any password. It's really cheap for me to send the data to you, and you have to compute 250, and every time that I send it, you have to consume 256 megabyte, and it takes that almost a second. What happens if I send you tens of those requests, hundreds of those requests? I'm not going to say 1,000 because the machine is already dead at this point. So the way that you typically handle that, you move some of that cost to the client because you want to share that cost. So the idea here is that you run the Argon 2ID function at the client side with really conservative parameters that takes some significant amount of time. But you don't do that but it actually is a multi-step process. The first thing that you do, you get a random seed from the server. And then the server then you compute what we call the PH, the password hash, using the conservative high-cost values. And then you compute it using a cheap algorithm with the seed that the server provided. The server then gets the computed value. It already has the password hash that previously computed, and it can do a much cheaper computation in order to verify what you're doing. And as I'm saying that, the only thing that pops to mind is maybe use an authentication provider and don't deal with that yourself. But you do want to understand how those sort of things work. So now we talked about secret key encryption, where you and me have a key, and we want to communicate with one another safely. The next step was password hashing, and how do you store and operate on hashing successfully. Now we talk about public key encryption. And public key encryption means that I have a public key and a secret key. And I have to be able to do certain set of operations. Signing, encryption, and decryption. Now, if I have the secret key, I can sign it. And if you have the public key, you can prove that I signed it. Anyone using the public key can encrypt a value and send it to me, but only I can decrypt it. So far, this is probably something that you already know. But let's talk about how you actually use that. So it turns out that this is used pretty much constantly. Because I want to talk to Google. Google apparently didn't bother to give me all of their secret keys. So I need to go to Google and establish that I'm talking to Google, negotiate a secret key with them. And if you're familiar, the typical algorithm is something like Diffie-Hellman. And then I can actually talk to them securely. This is how HTTP and TLS works. This is what we do all the time. But this leads to a really, really bad issue. I want to talk to Google, but in the middle, there is the network proxy for the hotel that doesn't want me to let to Google directly. It wants me to go and do some sign up. So how do I know? I put google.com in my address bar, and I'm trying to get there, but another entity entirely is answering me. How do I know it's not Google? I mean, they can give me here is let's do the Diffie-Hellman exchange and generate a secure key as well. So in order to do that, we go back to the notion of trust. And remember, public key can be used to encrypt data and to sign data. So here is how it works. There is a root that I trust. And that root is going to sign an intermediate certificate, which is then going to sign the final certificate that is being served to me by the website that I'm trying to reach. And the idea here is that I try to talk to Google, and the entity on the other side, which may or may not be Google, is going to give me a certificate. I'm going to verify that this certificate is signed by someone who I trust. And the easiest way to think about it, think about a passport. You have a passport, and it says who you are and all sorts of stuff like that. And the reason the passport matters is it because it was issued by someone that you trust, probably a government or something like that. So you have a transitive layer of trust. Eventually, okay, I'm trusting that the route that I have locally is not going to give Joe Schmo, any Joe Schmo, the certificate for Google. This is at the base of trust for everything in the internet. And it's really frightening because, for example, Google has their root certificates on all of your machines. So Google, for example, can pretend to be anyone it wants. In order to deal with that, there are really interesting mechanisms. For example, if for you to trust a certificate, the server needs to demonstrate that it was publicly published. So if Google is going to try to generate a certificate to a domain that they do not own, in order for it to be trusted, there must be evidence that they have done that. But eventually, all of this chain of trust is actually built on trust, which is really, really funny. Without using the public key infrastructure, also known as PKI, we have to have some other ways of doing that. For example, how many of you use WhatsApp? Anyone? Okay. How many of you actually ever validated the entity on the other side? There is a feature in WhatsApp that you can scan a QR code to verify that the other person that you're talking to, so you physically meet and you change your keys. And I don't think anyone ever did that. I mean, presumably it's a feature that exists for more than demos, but we have a relatively technical crowd, and anyone ever did that? I certainly never did. Yeah, someone did? Drug dealers do that? No, they do not. Drug dealer would use a special phones designed specifically for that by the police, because apparently, by the way, every time that you want to buy a secure phone, there are two options. Either you get it from a security agency such as your equivalent to the NSA, Mossad, KGB, etc., or this is a police sting operation. There is no middle ground. Go read the internet. There is a fascinating topics about people who are using a highly secure phone to discuss, and the government didn't even have to get a wiretap because they voluntarily gave them all of their information. But anyway, so you have WhatsApp and the ability to authenticate one another, and no one actually does that, but that's a side point. So this is public key infrastructure. But what do we actually use? There are two common algorithms. One of them is RSA, the other is X25519, which is referring to some ecliptic curve, which is some on a field that is some big on some big prime number. 2 to the power of 255 minus 19, if I remember properly. Now, it doesn't matter. It's math, and we trust the math. At least I trust someone actually validated the math. I certainly didn't. But here are the things that you need to understand about those things. First, RSA is really complicated to implement properly. In order to get proper security, you now need at least 258 or 4096 bits of security in order to achieve reasonable security levels. It means that your keys are big, the computation are huge. It also has another really nice property. In order to do RSA properly, you have to find two large primes. You know what the fun part about that? It takes quite a bit of time to do that, on most systems. If you need to generate an RSA key on a cloud machine, you can build, we had that scenario, we generated a RSA keys on initialization in a cloud instance. This was a burstable instance, and we burned through the entire CPU budget like that. And that sucks. On the other hand, you have X9919, and the idea here is generate a random number. That's it. There is nothing special that you need to do. And that's a lot less complicated and easy to do. So now we are at the key aspect of encryption. How do you manage the keys? Because at the end of the day, the keys are they are the keys to the castle. I have no other alternative. So a few things. It's really hard because it is effectively recursive. If you're using Windows, there is something called the DP API, Data Protection API, or DPAPI. And the idea here is that this is actually encrypted using a value derived from the password of the user, which is nice, until you have to reset the user password, and then poof, your data is gone. You can use a vault, you can use a hardware security mode or something like that, but in general, it really kind of hard to do so. And in most cases, don't try. Talk to your operations. There should be something that you already have available to you. Don't try to manage it in file that you square away somewhere or something like that. Really important, keys are generated through urandom, and don't try to do anything fancy there. But even more important, if you have a key, it's really trivially easy to derive additional keys from that. So you may use a single key. Oh, I need to sign some values, but I also want to communicate to you through secret cryptography to create a secret channel, encrypted channel. So never use the same key for multiple algorithms. There are no known weaknesses in doing that, but it is possible that there are. So you use a key derivation function to derive a separate key for each usage. For example, in RavenDB, we derive a separate key for every page that you use. In the catastrophic case that someone managed to hack us and the code was audited properly, they managed to discover 8 kilobytes of the entire database. That's the catastrophic scenario that we have because of key separation, key hygiene. And now it's time for questions. Yes. Yeah, sorry. Should you be worried about quantum machines? No, probably not. The reason that if you're using RSA today, you want to use keys with 2048 or 4096 bits of security. The reason for that is that quantum machines or quantum computing, if it's ever get to the point where it's actually practical, would have your security boundary. With something like AES 256 or XChaCha, those are both using 256 bits of security. And if they have that, you're at 128, which is still really big buffer. There are attempts right now to create a quantum-resistant cryptography. To my knowledge, there is no generally accepted algorithm that will replace AES, GCM, or XChaCha. And for communicating with public key cryptography, I would recommend using the X2219, the ecliptic cryptography, and not the RSA one. That's the general recommendation. In general, if you get to the point where someone is attacking you using quantum cryptography, give me a call. It is an amazing opportunity. Yes, more questions? Yes. I hear absolutely nothing of what you say. Can someone give him a mic? I can't hear him. Yeah. Okay, so the question is hashing with a salt. Okay, so the question is, if I hash a password with a salt, is it secure or not? The answer, it is extremely insecure and can be hacked in minutes. And the reason for that, if you hash with a salt, you didn't actually make it that much harder to compute to brute force the problem. Again, Hashcat can do 8 billion computation a second, and this is on standard hardware. If you go, Bitcoin did a number there. If you go to dedicated hardware, you can do even more. So you can say, oh, I have some random value, probably in the range of 8 characters, probably printable characters. Okay, and here is the salt that I have to use. Let's compute all opportunities, and I can even make it more easy for me because I can use the list of common passwords. And in very short order, you converge into the, oh, here is the value that gives me the same hash value, and that's fine. Oh, another thing that I forgot to mention, which is really important, look at the security API that you have. If you're using something like .NET, Java, Python, or something like that, they have a lot of history. And if you go and search for how do encrypt a string in C#, in Java, you are very likely to get results that are decades old, using API that still work, but are extremely vulnerable. The example that I gave with the cookie that you encrypt and it looks okay, but it's actually not because it's malleable encryption, is exactly that scenario. If possible, use modern systems. Look at the algorithm that you use. If you can do that, use something like libsodium, which is a very well respected and established library to manage your systems, to manage your security system and cryptography. Another thing that I haven't touched about is when you're dealing with security code, one of the things that you have to take into account that timing matters. For example, if I want to compare a hash, I computed a hash, I want to compare in the case of passwords. This is a good example. Where is passwords? So I computed this thing, the password hash with the seed, and then I compare it to the value that I got from the client. If I use something like memcompare or equal in C# or Java, this would effectively do, okay, let's do a for loop on the values and compare. Oh, it's wrong, let's go back. But the fact that I stop the computation based on the data means that externally I can observe that based on timing. So you need to use dedicated cryptographic API that are not timing sensitive. And again, if at all possible, go and use well-audited library and established solutions. The whole reason that I'm doing this talk is to give you the context for what exactly are we doing in this case and what you should not be doing. Any more questions? Yes? So, okay. So the question is, how do you encrypt very large files? ASGCM is limited, I want to say 256 gigabyte, after which you have to do something else. XChacha is not practically limited, something like terabytes or something like that. This is for memory, don't hold me up on that. There are two things, by the way, that you have to take into account when you worry about encrypting archives for a very long time. How do you store the keys? How do you ensure that the keys are actually safe? And this is actually a real problem. My recommendation, by the way, print it out and put it in a desk drawer. It is funny, but this is actually super secure compared to the digital world because it requires physical access to your location. So key management in this case is very big. In general, any security system that you would pick would generally be able to handle that. If you use Deep Sodium, it has API called Secret Stream that would handle key replacement, all of those sort of things for you without you having to really know about the nitty-gritty details of how it works. Yes? You're talking about, okay, so the question is, what about password-based key derivation for the encryption key? And you can do that. I would say I'm not happy about that. Because the password-based key derivation, this is when you have a list of words that you can memorize, and then you run some function in order to get a cryptographically secure result out of that. It works well enough to keep your Bitcoin wallet. It's not that ideal when you're talking about storing large amount of data because you want to have separate keys at all the times. So another thing that you have to take into account, okay, I'm rotating my encryption key on a regular basis. So I need to also remember all of the old keys. And eventually you don't put it in your head. And at some point you might want to look at a hardware security model, but then how do I make sure that there are backups? And this is a whole thing, and I will be very happy to talk about this later. Thank you very much. If you have any more questions, come to me afterward. Thank you.